On the last two videos, we start from the matrix A. What is the matrix A? Here you have AX equals C. This is a system of linear equations. A, the elements of A are the coefficient of the unknowns. X is unknown, the unknowns. Okay, now from A, we calculate A minus lambda I, the determinant of this matrix here, we impose to be 0, then we got the characteristic polynomial. Let's suppose lambda minus 2, let's put power 4 here, times lambda minus 5 to the power 2. Let's suppose. Then we calculate by inspection, okay, for each lambda, rho minus lambda I. For each lambda. In this case, it's for lambda is equal to, and for lambda is equal 5. This particular case. Then from here, we obtained the nullity nu, which is n minus rho. This here is the number of solutions of this equation here. A minus lambda I x is equal 0. This for each lambda. Okay. Now, from the multiplicity alpha minus the nullity, we get here the number of generalized eigenvectors. Without calculate them, we can build matrix J or matrix lambda. Sometimes I can obtain lambda, even if you have multiplicity higher than 1, as we saw before. Now, let's do this. In this video here, we are doing just the opposite. From here, we obtain the minimum polynomial. Now, in this video, let's suppose the input is the minimum polynomial. You see, we have the input. Okay, what we know now is the minimum polynomial. Also, what you know is the characteristic polynomial. Now, I would like you to pay attention or to remember, every time I write a minimum polynomial, this corresponds to a different matrix A. For instance, from here, okay, this is equal 0. Okay, suppose I start with this polynomial here. M of lambda is equal lambda minus 2 to the power 3, lambda minus 5 to the power 1. Suppose we start with this as input for our study. Now, there is a matrix A, okay, in which we obtain this minimum polynomial. Okay, now, suppose I have another, I will be working as an input with another minimum polynomial. Let's see this here. Then, this minimum polynomial, it came from another matrix A. Okay? Every time I write different minimum polynomials, this will correspond correspond to different a. That's okay? Now, then from here, how do I get minimum polynomial just to be an input to our study? Okay, who does this has to be patient, okay? Or you put in the computer to see. Let's do this. Now here, from Kelly Hamilton, for sure, a minus 2i to the power 4 times a minus 5i to the power 2, this is equal to 0. Okay? This didn't came from the minimum polynomial. This came from this input. Okay, this is also input. F of lambda, the characteristic polynomial, is also input. Now, let's suppose then we know the characteristic polynomial and we know one minimum polynomial. Now, you see, somebody did this, okay, by trial. What they did, they start with a minus 2i to the power 1 times a minus 5i to the power 1. So we have a matrix A, we have the two lambdas, you have this matrix here, a minus 2i, and multiply by a minus 5i. So suppose the result is a matrix different from 0. So this is not a minimum polynomial of this matrix A. Now let's do another test. You put 2 here and 1 here. Suppose it still is different from 0. So lambda minus 2 squared times lambda minus 5 is not a minimum polynomial. Now let's put 2 here and 2 here. Okay, suppose it still is different from 0. So this cannot be a minimum polynomial for this matrix A. Now I put 3 here and 2 here. Now it's 0. So the minimum polynomial will be lambda minus 2 to the power 3, lambda minus 5 to the power 2. This is equal 0. So when you work as an input, knowing the minimum polynomial, somebody made a test like this and wrote here, okay, for a specific matrix A. For another A, for instance, a to the power 1, a minus 5 to the power 1 could be 0 for another A. For another A, this square could be 0. So when I write a minimum polynomial m of lambda, you have to know that this minimum polynomial, somebody made a test, okay, like this, and they wrote down here. For a given matrix A, if you change the matrix A, probably there will be another minimum polynomial, okay? Clear, a given A, somebody made a test, and a minus 2i that multiplies a minus 5i, it was found 0 matrix. Then somebody wrote this minimum polynomial here. Now let's see what's going on here. Now m of such A is equal a minus 2i that multiplies a minus 5i. Now you have to remember this is equal to 0. You have to remember this is a power 1 and this is a power 1. You have to remember the blocks. The blocks. Look at here. When you have a matrix like this, lambda, lambda, and lambda, let's suppose. Okay, this matrix here is 6 by 6, okay, 4 plus 2. But let's talk about one such lambda, okay, 2. Then we have plus here. Okay, now, this is A, okay? Now, A is equal to this. Let's put A minus lambda, I. This will be 0, 0, 0, 0. You see, there is no ones over here. So there is no eigenvectors here. There is no generalized eigenvector here because A minus lambda I is equal to 0. Now, A minus 2I is equal to 0. You see, this is to the power 1. So I can write my J, A minus 2I or J minus 2I, okay, because A and J, they are similar. Like here is J minus 5I. Let's write J here. Okay, then I have 2 in the diagonal, 2, 2, 2, and 2. And 5 twice. 5 and 5. Now, A minus 2I to the power 1, this behaves as 0, 0, 0, 0. Okay, 0, 0, 0, 0 here. And here is 3 and 3. Okay, then I have 0, 0, 0, 0, 3, and 3. Because 5 minus 2 is 3. Now it's J minus 2I. J minus 2I. To the power 1. Now, let's write down J minus 5I. J minus 5I. Okay. I'll write down right here. Okay. Now, this is 2, 2, 2, 2 minus 5. This will be 2 minus 5 is minus 3, minus 3, minus 3, minus 3, 0, and 0. So J minus 5. Now, if this is 0, this is 0, this is 0, what this means? This means this. Okay. This means that my matrix J is equal to my matrix lambda, which is 2, 2, 2, 5, and 5. See here? Now, from here, okay, we built this just from here. Okay, this is a power 1. Now, from here, we can get the rank. You see? We can get the rank. Look, what is the rank? Let's put here. What is the rank of A minus 2I? Or the rank of J minus 2I? If I subtract here 2, I'll be 0, 0, 0, 0. So there is no pivot over here. Okay? But 5 minus 2 is 3. Let's write down. Okay? Let's write down J minus 2I again. Or delta, or sigma minus 2I. Let's put here. Sigma minus 2I. This will be 0. And this will be 3. I'll repeat again. I put here 0, 0, 0, 0, 3, and 3. This is minus 2I. How many pivots do I have here? I have one here and one here. I have 2 pivots, so this is 2. Now we can obtain all those parameters that I want to calculate number of eigenvectors, number of generalized eigenvectors, and I can, from now on, I can calculate p minus 1, and sigma. For what? To solve this equation. The difference between this video and the last two videos is this. Before, the rank was the input. Now, the minimum polynomial is the input. You see, from here you have ni, j minus 2i is equal. Now, this is a matrix, okay, have 6 by 6. Now, it's 6 minus 2, which is 4, okay, in this case. Now, and then we can calculate all we need to solve this equation over here. Now, let's lambda minus 5i. Lambda minus 5i. Let's put it here, lambda minus 5i over here. Okay. Lambda minus 5i. Here you have 2, this is minus 3, minus 3, minus 3, minus 3, and here will be 0 and 0. See? Okay, how many pivots do I have here? Okay. I have 1 pivot, 2 pivot, 3, and 4. So, row of j minus 5i is equal 4. So, ni will be, in this case, ni of j minus 5i will be the dimension 6 minus 4, which will be 2. Okay? From here, for lambda is equal to, you have for solution. Okay? Now we have for solution, look, alpha minus ni is equal, alpha is multiplicity, okay? 4 minus 4 is equal 0. So here there is no eigenvector, no generalized eigenvector. Here alpha minus ni is equal, alpha here the multiplicity is 2. 2 minus 2 is equal 0. Also here there is no generalized eigenvector, which we already wrote, okay, my lambda, because my lambda, capital lambda, is equal to 2, 5, and 5. There is no ones here, okay, which shows here there is no generalized eigenvector. For lambda is equal 5 and for lambda is equal 2. What is important is this. This is my input. From here, we obtain there. Let's do another example given a minimal polynomial. As I said before, we know a matrix A, another matrix A, doesn't have nothing to do with the example, the previous example. This is A, in which you have the same characteristic polynomial, and somebody made a test and found out that the minimum polynomial, or the matrix, is lambda minus 2 squared and lambda minus 5. So from here, you can write m of A is equal A minus 2i squared and A minus 5i. You see, this is just the opposite that we are writing here, just the opposite when you compare to the two previous videos. From there, we came from here to here. Now this is an input, this we know, that we can write here. Okay, this is 0. Now, what this represents, okay? Now, let's do this. I have a matrix A. Matrix A. Let's start with J, possible J, okay? J is similar to A. Let's put here 2, 2, 2, 2, 5, and 5. Now, J minus 2A squared is 0. So I'm investigating if I put 1 over here. If I put 1 over here and I do like this, J minus 2I is equal. Look the idea. This will be 0, okay? 0, 0, 0, 0. And this will be 5 minus 2 is 3 and 3. Now, if I put 1 here, okay, if I put 1 here, do you remember? If I square it, for sure, I'll get 0, 0, 0, 0. That's just remember the block. This is square is 1, 0, 0. So for sure, this will be this, okay? Then I know that this square, being 0, indicates me that I have a small block like that, you see? Now, if I square it, the answer of this will be, this is 9, okay, 9, 9, because I'm squaring. Okay, now it will be 0, 0, 0, 0. Let's put the diagonal. 0, 0, 0. Now, this will be 9 and 9, because I had 3 here and 3 here. So when I square it will be 9 and 9. This will be 0 here. That's my block. Okay. Also, one thing I can see here we have 3 blocks. So immediately I can write that ni of J minus 2I, for this case, is equal 3. See? Also we have 3 eigenvectors. If you have 3 eigenvectors and alpha minus ni, you see, this is 4. This is equal 4 minus 3 is equal 1. So I'll have 1 eigenvector which matches with this. This is only 1 eigenvector. You see how many parameters I can obtain just from this A minus 2I squared. See? Then I have a solution for this. Then I have rho is equal n minus ni. So rho is n minus ni. Now I know ni here, and n is 6. So this will be 6 minus 3. This will be 3. Now look how interesting it is. Look at that. This is not a row. This row here is row of J minus 2I. It's not row of J. Look at here. If I subtract 2 here, let's put it here again, okay? Here, look. I'll put 0 here, 0, 0, 0. This is 3. This is 3. Now, let's see. This is J minus 2I. J minus 2I. Now, let's see how many pivots do I have here. Okay? Now I have 1, 2, and 3. So, rho, the rank of J minus 2I is 3. Look at here. You see? Everything matches. But The same thing I'll do for 5, okay? The same thing. Now, let's see what I'll write here. Look. Let's see another possibility. Another possibility. Let's see here. If I write, this is 4, okay? Now, look, if I write my j is equal to 2, 2, 2, 5, and 5. You see, look, I'll put 1 here and 1 here. This is another j. The same minimal polynomial, okay, that put here. Let's see what I will have here if I put j minus 2i. Let's see here. You see, this will be 0, 1, 2, 3, 4. Now 5 minus 2 is 3 and 3. Let's put 1 here and 1 here. Now look, if this is a block, this is another, let's put here, here is another block. I can see here that in this situation, if I square it, this here times this matrix times this matrix, I'll have 0 here and 0 here too. Okay? Now, if I square it, I'll just erase this and I put 0 and 0. 0 and 0. Then I'll have here 0, 0, 0, 0. Here I have 0 here and 0 here, 1 block. Okay, this was 1 here, I have 0 here and 0 here, it's another block. Then I can write easily that n is equal to, because I have 2 blocks. And this square gave, and here is 9 and 9. 9 and 9. You see, look, a minus 2i squared, I have 2, for a while, I have 2 possibilities, okay? This 0, 1, 0, 1, 0, 1, 0, 1. So, from here, we can obtain row, okay? I could obtain row from here because I know n, I know how many blocks do I have. So, my row will be n minus n. N is 6. 6 minus 2 is equal to 4. Now let's see j minus 2i from here. What is the row of j minus 2i? Okay, if I subtract 2 here, it will be 0. Here will be 0. Here will be 0. Here will be 0. Here will be 3 and 3. 3 and 3. Okay, this is not a pivot, but this is a pivot. This is not a pivot, but this is a pivot too. This is another one, this is another one. So what is row? What is j minus 2i? What's the row of this? It's 4. Look at here. You see how I play with these parameters. From here and here, I will get alpha minus n. What is alpha? Alpha is 4. It's 4. N is 2. How many eigenvectors do I have here? I have 2 eigenvectors. How many generalized eigenvectors do I have here? It's also 2. Look, I have 1 here and 1 here. See? That's a very, very interesting. Now, you could think another one here. You see that we can put a 1 here. look, let's get another possibility, okay? Intentionally, I know the result, okay? You see that I can't put one here and one here. Let's see. Okay, let's put J. Okay, the same analysis I will do with lambda minus 5 to square, to the power, to the exponent 2, okay? Let's concentrate only in lambda is equal to. Now here, suppose I put J 2, 2, 2, 2, 5, and 5. Okay, the first J, see, those are different Jordan form. They are not equal. They come from the same minimum polynomial, a minus 2i squared. Let's forget for a while this. Now, here, the first one I put one here. The second one I put one here and one here. Okay, this is also a solution, okay? Because if I put one here, I'll have that block here. I have 3 blocks. Look, I do like this. You see? I have 3 blocks, so I have new here. Or I could put a one over here. But I cannot put 1, let's put 2, 2, 2, 2. I cannot put 1 here and 1 here. Why? Let's write j minus 2i over here, okay? If I write j minus 2i, I'll have 0 here. I'll raise, okay? I'll raise here. It'll be faster. I have 0, 0, 0, 0, 1 here and 1 here. This will be 3 and 3. Look, do you remember? This I have this block over here. This block. This block is different. This block, just remember, lambda, 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 and lambda. I have 4 lambda. I have here, let's see, this one is here, okay? Now I have 3 lambdas, okay? And I have 1 here and 1 here. Now this is A. A minus lambda I is equal 0, 0, 0, 1 here and 1, let's put there, and 1 here. Now, this block, this is the exponent 3 to the power 3 to the power 3, this is equal 0. Now, to get 0 here, I have to have j minus 2i to the power 3. But j minus 2i is to the power 2. That's why I can't put 1 over there. You see how our study is very, very deep, I would say, and interesting. Because, okay, I put 1 here and 1 here. It's okay, but I cannot put this. Because this I have 2 blocks here, okay? My input says that we should have j minus 2i to the power 2. That's why I cannot put 1 over there. You see? And this is a discussion about the input is the minimal polynomial. So the answer for this minimal polynomial will be j is equal 2, 2, 2, 2, 5, 5. J is equal 2, 2, 2, 2, 5, and 5. This is 1 here, okay? There are other j's here. I put 1 here, it's a solution. I put 1 here, is another solution. I put 1 here, is another solution. Just one, because to form blocks here. So from here, I have three different j's. Just play with ones over here, on the super diagonal. Okay, let's call one solution this. Okay, this is one solution, because if you subtract j minus 2i, this will be that famous block here. Okay? If I put one here, not here, but if I put one here, I have another block. So j minus 2i squared, this will be 0. This is one solution. Another one, I put one here and one here. I skip this one. I don't put one here. This is good also, because this will have 2 blocks here and 2 blocks here. Now 5 and 5, okay, I don't put one here. Why? Because a minus 5a to the power 1. You see? So I have 5 and 5 here. Here there is no generalized eigenvector for that. So these are 2 solutions. I would say here, this is J1, J2, I put one here, okay? J3, only one, I put one here. J1, J2, and this is J4, okay? That's a minimum polynomial, which allows me to, I will be able from here to write these different j's. Different j's, we have to have different transition matrix. As I told you, look, A is equal P, J, P minus 1. So if I change J here, I have to change P, the transition matrix, because the A is fixed. A is a matrix which I want to calculate that. You see? And from a specific J, you see, look, when I solve this equation, I have to choose one of these possible J. Okay? Let's suppose I chose J4. So then I have to build P4 and P4, the inverse, to find A. Now suppose I want to pick, to use J1, then I have to put here P1, J1, P1. So what this can allows me to calculate the number of eigenvectors, because I can find row here easily. Row of what? J1 minus 2i. If I subtract 2 here, okay, this will be 0. Okay. This will be 1 pivot, 2 pivot, 3 pivot, because this will be 0. From 6 and the row, I can get the number of eigenvectors. If I subtract the multiplicity minus ni, I get the number of generalized eigenvectors. So I can solve this equation. You see, I have been demonstrating, showing that the objective is to solve AX is equal C. It's not to write a Jordan form. It's not. Now, another one, suppose a system of linear equations, somebody wrote A, different A from the previous case, wrote A. Then he obtained the characteristic polynomial. Suppose this is equal to 0. Now, he tested all the possibilities to write this equation, this equality here. He found out that a minus 2i to the power 3 times a minus 2i to the power 2 is equal to 0. He tried. This is a test. Now, from here, how can I build J? Now, let's see. Then I'll put here j is equal, let's see, 2, 2, 2, 2, 5, and 5. Okay, now, here is a power 3 that is 0. So remember, you have always to remember these blocks. They are very important for you to see what's going on with a minimum polynomial. Look, I have lambda, 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 one here and one here. I cannot put one here, please, because suppose this is 3 by 3. If I put one here, I have 4 columns, so there is no one here. All of the number of ones is n3 minus 1, always. That's called Jordan block, when you have 1 and 1, okay? It's filled, all the elements of the superdiagonal are all ones. Now, if I subtract lambda here, a minus lambda I, this is 0, 0, 0, 0, 0, 0, this is 0, I'll put here 0, 0, 1 here and 1 here. Okay, if the exponent is 3, this is 3, for sure this will be 0. So, knowing this, I must have 1 here and 1 here. See? Because when I subtract 2 here, I have the minimum. Okay, 3 here is the minimum exponent. Obviously, if I put here 10, this will be 0. So 3, if I put 2 and 2 here, this will be different from 0. To be 0 has to be 3 and 3. That's a minimum exponent such that a minus lambda I to the power 3 is 0. Now, if I can see, okay, that I have to put 1 and 1 here. Another j could be like this. Look, I could put 1 here and 1 here. You see here, you look at here, when I subtract 2 and look at that, it's the same. So, then I have 2 possible j's here. Is 1, 1 here. Now, I'll have here 2 blocks. One block. Okay, look at that, just 1 block and this 2. From here, I could write, okay, that lambda is equal to nu is equal to. From here, I have 2 blocks here. Okay, I can see. Okay, 1 block is this block. Subtracting 2. So, from here, I know that j minus 2i, j is similar to a. Okay, this a is different from the previous example. Please, it's another j. Now, this is the power 3. I'm sure this will be 0 here. I'm sure. Okay. This will be 0. Let's write down here. I will erase this. It's faster to do this. Okay? I put here 0, 0, 0, 0. 5 minus 2 is 3 and 3. So, here we know in this block here, this is 1 and this is 1. You see, look at here and look at that. Okay, the same. Okay. Now, this is the power 3. This will be 0. So I have here a big 0 here that corresponds to j minus 2i to the power 3. Now, this is 3. This is 27. 27. Okay? Now, let's do as follows. J minus 5i to the power 2 is equal to 0. let's put here, okay, j is equal, let's put 2, 2, 2, 2, 5, and 5. Now, this is square. Look, if you know these blocks, it's very simple to write here. Look, I have a square here. This has to be 0. So I have to put 1 here. Why? Because when I subtract, so I have here 1 here and 1 here, okay? I have j like this. Why do I have to put 1 here? Because here is squared. Okay? When I subtract 5 here, I will be 0, 1, 0, 0. So if I square it, this will be 0. So let's do it. Let's do it. Yeah? Let's do it. See? Now, let's write j minus 5i. Look, 0, I'm sorry. 2 minus 5 is minus 3, minus 3, minus 3, minus 3. This will be 0 here and put here. 0 here and 0 here. You see my 1 here? You see my 1 here? If I subtract, look, if I square it, this here will be 9, 9, 9, 9, okay? And this will be 0. So if I square it, I will raise, okay? Look, this will be 9, okay? 3 squared is 9. And this will be 0. So I come up with plus 9, 9, 9, 9, 9. Here I have 0, 0, and I have 0 here. You see this block? This came from 0, 1 and 0, 0. Squared, this will be 0. Okay? This is j minus y to the power 3. Now, as I said, okay, in the last video, these correspond to lambda, this 0 here, correspond to lambda is equal to. This here correspond to lambda is equal 5. This here correspond to lambda is equal 5. And these numbers here, different from 0, correspond to lambda is equal 2. So if I multiply this times this, okay, this 0 here will multiply by the 999 will be 0. And 27, 27 multiplied by this block here will be 0. Okay? Then, I'm sorry, this here is 1 here, okay? Let's put it here. I forgot because it's 5. Oh, I'm sorry. Yes, it's 5, 5. Okay? 5 minus 2 is 3. Okay? This is 1 here. Okay? Now, this is 1 here. Okay? Now, you see how it's easy to see it. Okay? From here, from j minus 5i, we know the rank. From j minus 2i, we know the rank. Okay? And also number of blocks. Here I have 1 block. Look. So for lambda is equal 5. We know that must be 1 because I have only 1 block here. You see? For lambda is equal to I have 2 blocks. See? I have 2 blocks on here. So if I write, then I can obtain the rank, the nullity, the number of generalized eigenvectors. I can have everything. And with the rank, we can solve with the rank and using the number of eigenvectors, we can calculate, okay, and get matrix P. So here I could write, okay, the other solution. Yeah, that's the same thing. Okay, j minus 2i, I could set like this. Let's write down here. Okay. It's the same thing. I put here 0, 0, 0, 0. Remember, I put one here and one here. Now I can put one here and one here. It's the same thing, you see? Same. Okay? The same here. I still have 2 blocks here. And also here, I have 3, 3, and 1 here. Because 5 minus 2 is 3. This is a block for lambda is equal 5. There's a block for lambda is equal 2. See? Now, the same thing. Okay, I get the same. Look, if I square it, I'm sorry. If I power this, the power 3, this will be 0. Okay? This will be 27. Okay? Then I take j minus 5i. Okay? This will appear 0, 1, 0, 0, the same there. So if I square it, it will be 0 here. Okay? It's very, very easy. Okay? Let's suppose there is a linear system, a system of linear equation. I obtain my A is different from the A's from the last example. Suppose have my A, I get my characteristic polynomial is the same. Suppose each characteristic polynomial from different A's, suppose are the same. Then somebody tested and found out this, okay? And he wrote, this person who wrote the minimum polynomial, this is equal to 0. Okay, now from here, j is equal. Is 2, 2, 2, and 2. This is 5 and 5. This to the power 1. Okay, the power 1. Because the power 2, this investigator, okay, just should use Cayley-Hamilton and know that the a minus 5 over power 2 is 0. So he tried this. He tried. Okay, let's see. And this, there is no 1 here, okay, because a minus 5i to the power 1. So there is no generalized eigenvector. Now, here I want for this to be 0, so let's come here, lambda, 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 lambda. This is 1, 1, and 1. I have 4 lambda in the diagonal, and the super diagonal is 4 minus 1 is 3. Again, I cannot put 1 here because I have 4 columns from here. If I put 1 here, I have 5 columns. Okay? Always, this is called Jordan block. When I put all 1 here, this is called Jordan block. Now, what is the minimal exponent for this? Not for this, but for this. A minus lambda I. This is equal 4, 0 here. I have 1 here, 1 here, and 1 here. This to the power 4 will be 0. So, from here, I can write 1 here, 1 here, and 1 there. You see, if you subtract 2, you see that right here, j minus 2i is equal, this will be 0, 0, 0, 0, 3, and 3, because 5 minus 2 is 3. Let's fill this with 1 here. You just look, okay? Look at here, and look at here. The same thing. See? Same. Now, you see that for lambda is equal to, I have only 1 block. Then I can write mi is equal 1. Okay? No, 1. Okay? Now, if I put the exponent to the power 4, this here will be 0. Okay? From here, okay? This will be 0. And 3 to the power 4 is 81. Okay? I'll erase and write now. Okay? I'll erase it. Then here will be 0, 0, 0, 0. This was 1, now the 0. This was 1 is 0, and this is 0. This is 0. So 3 to the power 4 is 81. 81 and 81. See? Attention here, 81, okay? This is not a 1 close to 8, okay? This is 81. Now, this is 0, okay? This is 0, which this indicates that this is 0, see? And a minus 5i, I put 0 over here. If I write j minus 5i. When I multiply, I have this to be 0. What's important is this. Look, this is one block. Now, from here, I can find rho for j or a minus 2i, just easily, because n is 6, okay? Then it's 6 minus n, 1 is equal 5. This is equal 5, okay? Now, let's see one thing here, okay? This is 1, 2, 3, 4, 5. You see, j minus 2i, okay, write down here j minus 2i, j minus 2i. Let's see, this will be 0, okay? I'll raise here, put 0. I will raise here, put 0, and put 0, okay? Now, this is 3 and 3. Okay? Now, this is not pivot, okay? This is 0 here. This is 0. This is not 0 because this is 1. 1, 2, 3, 4, 5. 5 pivot. Look at here. Look. 5 pivot. Okay? If with rho and ni, we can get alpha minus ni, okay? So what is alpha? Alpha is 4, minus 1 is 3. I have 3 generalized eigenvector. Look, how many ones do I have here? 3. See? Now, do you remember when I said in the previous 2 videos that the minimum polynomial that help us to find the solution of this equation? Look, here the minimum polynomial is helping us because from here I can write down nu and rho. But what I said is this: we don't need to know the minimum polynomial. Look, if I have my matrix A, and if I have the characteristic polynomial, I can count the number of pivots of A minus 2i. In my viewpoint, this is much easier than to try to make tests and find out what is the minimum polynomial. So, you see, I have matrix A. I have my characteristic polynomial. Okay? Then I can write or calculate A minus 2 lambda I. Okay, that's a matrix. Then I see how many columns are linearly independent. Must be less, okay, than the dimension, as I said before. With the rho on my hand, okay, I calculate ni and calculate alpha minus ni. So then I solve the equation A minus lambda I x is equal 0. I know how many solutions I will have on this equation. And also I know how many generalized eigenvectors. That's I said. I don't need to know the minimum polynomial to solve this equation. That's what I said. But minimum polynomial, if you open books and videos, they talk about the minimum polynomial and do a lot of things with it. But to solve this equation, we don't need. Okay? For me, it's cumbersome, I think. It's boring. That's better. It's boring to try to make tests and find out what's the minimum polynomial. Okay? It's boring.